Hi, welcome to DfRSoft's instructional video on mixed failure modes plotting in DfRSoft. I'm Dr. Alec Feinberg, and this tutorial should be instructive even if you're not using DfRSoft. So when you have mixed failure modes, your CDF, your cumulative distribution function, has a certain proportion of each failure mode that takes up the distribution. For example, if you have two failure modes, this may take up 30%, the early life failure modes, and so the next one would be 70%, 100 minus the 30%. So let's look at how that might be. Here's an example of that. Here's two distinct distributions, an upper and a lower modes. This is a probability plot, the CDF, the cumulative probability for failure, versus time. And this is the percent that has failed over time. And here's our data right here. We also notice that we have 18 suspensions in our units. So the upper population, you can sort of see the inflection point, and the inflection point is a very important thing to know about. Let's talk about the inflection point for a minute, because you have to identify the inflection point. If you don't see an inflection point, then there's no reason to try to separate out the data in general. So some of the fancy routines that you're using, if you're using and separating out failure modes that you can't see the inflection point, there's a chance that you should need to do that. So often in live testing or field data, a subpopulation and a main population are observed, occurring at two distinct time frames. The subpopulation, sometimes called freaks, shows up early in test time or maybe in the field, compared to the main failure population. Sometimes you see this S shape. That makes it easier to separate out. Now let's have, as an example, in a semiconductor, for example, you might have a diffusion failure mode, which could take a long time to fail. It could be in the wear-out region, where you might have wire bond cracks. Some portion of your semiconductors may have gotten cracked during wire bonding, and they might fail very early in the field or on life test. So that's why those occurred at a different time frame. So let's go over to DfRSoft and see that. Here's DfRSoft, the application. And you see that this is the welcome page. You have the reliability, quality, engineering, and physics of failure tools, so we can hyperlink over to the reliability tools. And this is our open style reliability type of menu. Down here you can see like field return areas that you can go to, reliability plotting, the types of reliability plots you can go to, or system reliability, block diagrams or NFK and things of that way. Down below is your quality tools, lot sampling, Six Sigma, CBK, availability and sparing, engineering tools like thermal analysis, conversions, vibration and shock, corrosion, electrical, and your physics of failure library. It's not a very expensive tool. All this for $285, so you get an incredible amount of stuff. So now we're going to hyperlink over. There's two modules, 2 and 3. Module 2 is for reliability plotting when your suspensions occur at the end of test or all your units fail. Where Module 3, your suspensions can occur, which are good units that occur anytime. You can use that in Module 3, and I'll show you that as an example. So we could have hyperlinked over. For example, we can just go to Module 2 and hyperlink over. Or you can tab over down below here. All the modules are numbered, as well as there's a label for each one. This is the rel plots, and this is your SRel plots. Where the SRel plots, as I mentioned, the only difference is in the SRel plots, you have to tell it whether it's failed or not, whether it's F is for failure, S is for suspensions, so the name SRel plots. Now in the rel plots area, you don't have to put an F or an S. All the units that you put in are assumed to have failed. And the way you handle suspensions at the end of the test is by putting it in this square right here. I'll remove it for a second. So we have 18 units that suspended at the end of test, so we can put them in there. And you can see what occurs here. And if the good units are removed at a later time, you can put the later time there as well. If you don't put a later time in, it'll assume the last month is when they were removed. So we're going to do that. So the first thing we want to do is to look at I'm going to look at our results, and the results here are shown here. Here's the regression analysis. These guys here are the popular distributions, the Weibull, log normal, exponential, 3-parameter Weibull, and also the maximum likelihood estimation. And all the results are to the right. And we're going to go over to the regression one because most people are familiar with that. And you can see that the data is not a very good fit. The data points are in blue. The regression analysis is in green for the fit with the confidence bands. And the results are right above the plot, giving the beta, the characteristics life, the MTBF, and your confidence bands that you select, and the type of confidence. So we now know that we have this inflection point, and we start off by removing the upper population. We're going to iteratively go and you can do as many modes as you think are in your data in DfRSoft. So we're going to first separate out the upper modes, and then we work our way down. So this point is right around 42, 43%. So now we have to tell DfRSoft where the inflection point is. Here is the mixed modal analysis in this column, in these columns right here. Now DfRSoft doesn't know where the inflection point is. You have to tell it from your visual. As I mentioned, if you don't see a inflection point, it's probably not of interest to do this kind of exercise. So you would put that right here, your inflection point. DfRSoft just separates out your data by proportion to the number of units you have and finds roughly the midpoint. So we're going to tell it 43%. So it renormalizes your data. So the lower population goes to close to 100% because we're plotting the medium plotting position, so you don't really get to 100%. The upper population, you see, it only goes from 1% to 18%. Now, why is that? Why don't you renormalize to 100%? Well, it is. The only difference is you have these 18 suspensions that we put in. So that's a lot of units at the end of test, and those 18 suspensions are in the upper population, are considered to be in the upper population. So now how do we get to the results? The results are, you can hyperlink down over. There's a little hand here. You hyperlink over. It's just down and to the right. So we're hyperlinking on the same page, and we'll zoom out just a tiny bit, and you can see the results. Here is your early life failure mode separated out. That's your freak population, normalized to 100%. And here is your later life population, and here is the original data set that we found the inflection point in. And your results are right over here, so you can see that results. The later population has a beta of 2.9 and a characteristic life of 113 or 14 months, where the early population has 0.88, so the beta is less than 1. It's infant mortality. The characteristic life is 7.3 months. You can see those are your early life failures. So it kind of makes sense, everything. Now you're ready to to further iteratively separate out your next failure mode. So let's hyperlink back, or you can just go up and over. And so what we want to do is you get the same results, by the way, in SREL plots. Or you could here's SREL plots where we can hyperlink over to the results, and you can see it's the same kind of thing. Results are identical, just a different way of plotting. So the next thing to do is to remove the upper population, and we can see that occurs at around 27%, rather the 27 number. So I'm going to start removing those data points. And you can do this a little faster. You can turn off the calculator in DfRSoft, and you can remove the data and change it a little bit faster. And there you have it. The data is removed, the upper population, and So we are now able to look at and see if we have any more failure modes that we want to separate out. And yes, there's another inflection point. So we could actually start this maybe around 35%. So we could iteratively remove this. We can start looking at these two populations, and maybe there's another one down here. So you can separate out as many failure modes as you see in the population. So that's basically it. Thank you for listening to the presentation of how to iteratively remove mixed failure modes from your life test data or your field data.